to have a matrix with all the elements equal to 0 except the elements that exist on the principal diagonal. So one of the advantages of having a symmetric matrix and getting the eigenvalues and the corresponding eigenvectors is the ability to get a diagonalization for this matrix. With the elements on the diagonal are the eigenvalues of this symmetric matrix. This is the symmetric matrix that we were talking about. Okay. Remark that based on the sign of the eigenvalues, assuming that we already succeeded in evaluating the eigenvalues. We will go through how to evaluate eigenvalues. You will remember them. It's very, very simple. But regardless on how to evaluate them at the time being, if we could find them, okay, depending on the sign of these eigenvalues, we can determine the classification of this quadratic function, if it was positive, definite, semi-definite, and so on. So first of all, if you have all the eigenvalues positive, all of them are positive, you will have a positive definite quadratic form. If positive semi-definite will happen when one of these values are non-negative, so some of them positive and the others, and one of them equal to 0. Are you reading me? Okay, so, and also the same, if all the eigenvalues are less than 0, you will have negative definite. And if they are non-positive, which means one of them may be 0, then you will have negative semi-definite. Are you with me? Okay, but if you have mixed values of eigenvalues, then you will have indefinite quadratic form. So now I have the second tool. Now, for the time being, I have two tools to use. Either the coefficients of the quadratic form, if it works with you. Otherwise, you will need to get the eigenvalues of this symmetric matrix that you succeeded in getting it from the quadratic form. Are you reading me? Okay. Now, I will come to the point of how to evaluate eigenvalues. Remark that based on the eigenvalues, we succeeded in determining the type or the classification of this quadratic form. Are you with me, Dina? So, regardless of how to evaluate these eigenvalues, now I will take a dive with you into our memories on how to evaluate eigenvalues. Okay, it's really very simple. Okay, we will get back to many slides shortly. Let's do this example, which is really very simple, just to refresh things on how to get an eigenvalues. If you look to this matrix, what do you see? If you look to this matrix, huh? It's a symmetric matrix, am I right? Can you write the quadratic form assigned to it? Can you write the quadratic form relative to this matrix? If we are dealing about x and y? Yes, it's going to be, if you like, 9x squared, and then 4xy, and then more than perfect. More than perfect. So from quadratic form into a symmetric matrix, or from the symmetric matrix into quadratic form, it's really very simple. Okay? Now I will have to get the eigenvalues, I will get the corresponding eigenvectors, I will get what's called orthonormalized matrix, which have the luxury of being an orthogonal matrix, which means its inverse, its transpose is its inverse. This is in the depths of linear algebra, of course. And if you multiply U transpose this matrix into A, the given one, times U, you will have a diagonal matrix. Let's go through this in details. Just let me check about the camera, how, just a second, please. Okay, I want to be sure about the area on this whiteboard covered with us. Okay, perfect. I want to start simply with taking the determinant of A minus lambda I, and I will put it equal to 0 in order to get the corresponding eigenvalues. So all I have to do, Princess Dina, is I'm going to open a determinant, writing these values, which are 9, 2, and 2, and 6. And put this determinant equal to what? To 0. Then I will take minus lambda from the principal diagonal, because you have minus lambda times a unit matrix, which is 1, 0, 0, 1. So it's going to be minus lambda minus lambda. Are you with me? So the second step, this is an equation. Try to expand this equation and simplify it. How to get the value of this determinant? I will multiply the elements of the principal diagonal minus the elements of the secondary diagonal, which means I will have 9 minus lambda times 6 minus lambda minus 4, and all of this equal to 0. This is the first step. Then trying to simplify life a little bit, so it's going to be a lambda square minus, I believe, 15 lambda, am I right? Plus a 54 minus 4 equal to 0. And this will lead you to have lambda square minus 15 lambda plus 50 equal to 0, which can be factorized, I believe. We are looking for two numbers, their multiplication equal 50 and their sum equal 15, which is 5 and 10, I believe. So it can be factorized like this. This is lambda minus 5 minus 10, and both of them equal to 0. Are you with me? So I can go whatever you like. I like to take the smallest value for lambda 1. So lambda 1 equal to 5. There is no regulations on this. It's just my personal preference. That's it. Lambda 1 equal 5 and lambda 2 equal to 10. Are you with me? Now at this point, I can classify the type of this quadratic function or this quadratic form, which is going to be a positive definite. Am I right? Both of them are positive. Okay, but I need to review with you how to get the eigenvalues and how to get the corresponding eigenvectors, and if needed, how to take a diagonal matrix. So this is the first step. By evaluating the eigenvalues, I can now be sure that this function is positive definite. So from here, I know this quadratic form is positive definite. Am I right? Okay, how to get the first, before going further, now I can answer the algebraic multiplicity. How many times 5 is repeated? 10. How many times it's repeated? So this is both of them have an algebraic multiplicity of 1. Keep it in mind. Okay, I will go to get U1. Now, we will go to get U1, the first eigenvector, which is corresponding to lambda 1, which equal to 5. All I have to do is to take this value and substitute in the matrix or in the indefinite solution or the homogeneous equation by this form. So all I have to do is to replace lambda by 5. So I will have 9 minus 5, 2 and 0, because I have a homogeneous type of equations. For the second row, it's going to be 2, then 6 minus 5, and as I told you, it's a homogeneous type of an equation. Once you do this, it's a must to have this matrix. You will have a 2 by 2 system of equations, and for the first row, you will have 4, 2, and 0. For the second one, it's going to be 2, 1, and 0. Stop. At this point, once you are using lambda equal one of these lambdas, you will have an infinite number of solutions for this system of equation, if you remark. Because these two rows, either they are identical or there is a ratio connecting these two rows. This is a must, because you are using the values of lambda that came out from the determinant which equal to 0. So it must happen. These two rows must be the same, or there is a ratio connecting these two rows. I will try to get to the reduced echelon form in order to get a successful solution of this system. How to get to the reduced echelon form? I will need this guy to equal to positive 1. How to get this guy to equal to positive 1? I will multiply the first row by a quarter, okay, by 1 over 4. So if we multiply the first row by 1 over 4, we will end up having 1 and 1 over 2, am I right? Then 0. Then I will need this number to equal to 0. How to force this value to be 0 in this matrix? I can do this by multiplying the first row, yes, by this element but with opposite sign. Do you remember the row operations in matrices? What are they? Replacing rows, yes? Multiplying one complete row in a single number or in a constant, then adding it on another row. This is what I'm doing. Okay, or multiplying a complete row from the beginning to the end in a certain number. This is actually what we did. In the first step, we multiplied the first row by 1 over 4. So 1 over 4, you will have 1, and you will have half equal to 0. And for the second row, I will multiply -2 and adding on the last row. -2 plus 2, you will end up having a 0. -2 times half is going to be -1 plus 1, it's going to come up to 0. -1 times 0 plus 0, so it's going to be a 0. Now, I have the simplest form and the most nearest form to a row echelon matrix. Now I will try to expand. This is going to be the first vector, first component. First vector, second component. Start expanding. 1 in U11 plus 1 over 2 in U12. And both of them equal to what? To 0. So I'm expanding the first row as an equation. The second step, which means U11 will equal to -1 over 2 U12. Are you still with me? Now, I'm saying that the first eigenvector consists of two components. One of them U1 sub 1, the second one is U1 sub 2. Now I can replace one of these variables by the value of the other. I can replace U11 by -half U12. So it's going to be -half U12 with 1 degree of freedom. This is 1 degree of freedom. It depends just only on the choice of U12, am I right? So once it's 1 degree of freedom, it means a geometric multiplicity of 1. You have algebraic multiplicity of 1, geometric multiplicity of 1, so the condition is correct. Now, just choose any value from U12, any number that you would like. I would recommend choosing 2 instead of U12. Why 2? Why is specific? Considering U12 equal to 2. Because I will get rid of half. Am I right? Are you with me? You read me? Okay. So start like this. Considering U12 equal to 2, this is gonna lead to this vector, which is gonna be 2 minus 1 over 2, so it's gonna be a negative over 1, and therefore this value is gonna be 2. This is what's happening to get the first eigenvector. I will redo all of these steps once more. But this time, in order to get U2, which is the eigenvector corresponding to what? To 10. How to get it? Remember, okay? Get lambda 2, which is 10. Similar manner to the previous steps, I will do it once more. But instead of putting lambda equal to 5, I will use lambda equal to what? To 10. Start substituting. 9 minus 10, I will write it first, 9 minus 10. Then I will have 2, and this is 0. For the second row, it's a 2. 6 minus 10 and equal to 0. Are we okay? Then go for the next step. The next step will be, I will have the following. 9 minus 10 is going to be a negative of 1. This is 2, and that's a 0. Then negative 1, this is going to be a 2, then a negative 4 and 0. Can you remark? There is a relation or a ratio connecting the first row and the second row. Yes? If you multiply the first row by -2, you will have the second row. All I have to do is trying to get as much close as possible to the reduced echelon form. So I will divide with -1, so I will have 1, -2, and 0, dividing by -1. Then once more, I will multiply by -2 and add on +2. Let's do it. -2 plus 2, Negative 2 times negative 2 is going to be positive 4. Plus negative 4 is going to be 0 and 0. Are we right? Now I will start to do this step once more. Now I'm targeting U2 first component, U2 second component. Am I right? Start expanding. 1 times U21 is going to be U21. Negative 2 times U22 is going to be negative 2 times second vector, second component equal to 0. Which leads to that U21 will equal to U of 2 sub 2. Now I can write this eigenvector once more, which is the second vector first component, the second vector second component, start replacing from here this value, so it's going to be a 2 in U2 and 2, and this is U2 and 2. Choose any value that you like. I will choose positive 1, so I will have the eigenvector which is 2 and 1. This is the first eigenvector, and that's the second eigenvector. Are you with me, Dina? If you remark, this is also, it's a 1 degree of freedom. Am I right? So just only U21 will depend on the values of U22. So the geometric multiplicity is also 1. This is what we meant about the algebraic multiplicity and the geometric multiplicity. Okay, done. Now I need to get the orthonormalized model matrix or the orthogonal matrix related to this given symmetric matrix. It's really very simple. All I have to do is to open a new matrix, and this matrix will contain the U1 in the first column and U2 in the second column. So for the first column, I will have negative 1 and 2. For the second column, I will have 2 and 1. Dina, do you remember that within the first matrix, I choose U12 equal to 2? Am I right? And in the second matrix, you choose U22 equal to 1. I can use it at 3, and here is I can use 6 or something. So I need it to be on a unit matrix form. Or these vectors, I need them to be unit vectors. How to change a vector to be a unit vector? Simply by dividing its elements on its magnitude. How to get a magnitude of a vector? It's simply the square root of the sum of squares of their components. Do you read me? So you check your head and start to worry. Okay? Now I will need to get the magnitude of U12, which is simply the square root of the first component squared. So it's a negative 1 to the power of 2. Plus the second component squared, which is 2 to the power of 2, which is going to be root 5. Am I right? Similar manner, if I want to get the magnitude of U2, it's going to be, this is the magnitude of U1. So the magnitude of U2 is going to be also exactly the same. It's a square root for the first component to the power of 2 plus the second component to the power of 2, so it's going to be a root over 5. This is just a coincidence here. So all I have to do is to take these elements and divide this vector on its magnitude and that vector on its magnitude. It's not a condition that they will have the same number. But here it's a coincidence, okay? So all I have to do now is to check what he wants. So this is actually the orthogonal matrix that we are dealing with. Negative 1 over root over 5, 2 over root over 5, this is 2 over root 5, and that's 1 over root 5. Remember, for this orthogonal matrix, its columns are vectors, and they are orthogonal. Do you know the condition that two vectors are orthogonal in each other? If you do a dot multiplication, the result will equal to 0. Remember. Negative 1 times 2, negative 2, plus 2 times 1 is going to be 2. The sum of them is going to equal to 0. So its columns are perpendicular in each other, are orthogonal in each other. See, it's a magic. For this matrix, which is the model matrix, if you multiply, let's first of all Let's get the transpose of this matrix. So U now is -1 over root 5, 2 over root 5, 2 over root 5, 1 over root 5. Let's get the transpose of this matrix. If I got the transpose of this matrix, it's going to be -1 over root 5. I will move this guy here. So it's going to be 2 over root 5, 2 over root 5, and 1 over root 5. If you multiply these two matrices in each other, you will get a unit matrix. And if you multiply them sandwiching A in between of them, you will get a diagonal matrix. I will do this, okay, on the screen. So these are the steps in order to get an eigenvalue, eigenvector. If I have the eigenvalues, I will be able to determine what I need. I did go through all of these steps just to complete the revision about the eigenvalues and the eigenvector to make you remember this. Okay? Okay. Once more, here's 9, 2, 2, and 6. I will get the eigenvalues for the spectrum. It's very, very simple. I'm getting the determinant, which equal to 0, a minus eta I or lambda r. As I told you, it's going to be like this determinant. I will expand it once more. So multiplying the principal diagonal minus the secondary diagonal. Trying to make things easier, I end up having eta squared minus 15 eta plus 50 equal to 0, which can be factorized, leaving us with eta 1 equal to 5, eta 2 equal to 10. At this point, now I know it's a positive definite quadratic form. If I want to get the eigenvalues, it's going to be, the eigenvectors is going to be simple. All I have to do is to solve the homogeneous system A minus EI U equal to 0. This is why I will deal with this system of equation. Exactly in a similar manner for eta equal 5, 9 minus 5, 2 and 2, 6 minus 5, and zeros. Here's what I have. I have two rows, they are similar to each other, or there is an anchor between them. All I have to do is try to get as close as possible to a reduced echelon form. Already succeeded. Now I have U11, 0.5 U12. If you try to expand it, you will have the relation connecting them together. U11 equal negative half of U12. Now I can write the first vector, which is U11, U12. I can replace U11 by negative 0.5 U12, I bet. Choosing a value for U12, whatever you like. Here I would suggest using B2 because 2 times 0.5 is going to equal to 1. I did that already. That's the first vector. Redoing the things exactly the same, but with eta equal to 10. This is going to be the system. I will replace just these two guys with 10. So now here we go. Two rows exactly the same, or there is a ratio between them. I will try to, as I did previously, trying to get as much as possible to a reduced echelon form. Now I have U21, negative 1, U22 equal to 2. Expanding them will give me the length that I will need in expanding my vector. This is U12, U22. I will replace this guy by 2U22. Here we go. Choosing a value for this free variable, which is going to be 1. I had U2, which is 2 and 1. Remark, these two guys are perpendicular in each other. Because if you did a dot product, the first time, the first, second plus second, will equal to 0. These are the two vectors. Second step, getting them on a unit vector type. This is going to be the U matrix. If you get its transpose, if you multiply them together, U2 minus U or U minus U, I'm sorry, U2 times U or U times U transpose, you will have a unit matrix. Boss, it's really very simple. Multiplying the first row by the first column. Negative 1 times negative 1 is going to be 1 over 5. The second element by the second is going to be 4 over 5. This is equal 5 over 5, which is what? Then the first row times the second column. It's going to be negative 2 over 5, and the positive 2 over 5. And their sum will be 0. So really, when you check that, you will end up having a unit matrix from the same dimension. This is one of the advantages of using this orthogonal matrix. Its transpose is its inverse. Do you understand what I'm saying? So this matrix, once more, this matrix, U matrix, it's an orthogonal matrix. What are the orthogonal matrices? The transpose of these matrices is its inverse. Once elliptic transpose, it's going to be the inverse. How to check it is the inverse? If you multiply them together, it's going to be a unit matrix. Here we go. That's a unit matrix. The most important property about this is to get the diagonalization. How to get the diagonalization for? Simply, this is the U transpose, this is the U matrix, sandwich them by the A matrix. Here we go. This is the matrix that we had from the eigenvalues. It's transpose sandwiched with the A matrix. If you make this multiplication, multiply these two guys first, then the result will be multiplied in the third one. This is what you are going to get. بص يا دينا سبحان الله سحر. خلاص انا هديك ستوب دلوقتي. بصي once you make the multiplication, you will end up having a diagonal matrix. This is what's called a diagonalization. With the elements of the diagonal are the eigenvalues. Are you with me, ready? Okay, done. This is all about the eigenvalues that we spoke about previously. That's another problem about the eigenvalues. I will continue this after a short break. What's the time being? I will give you a short break at the time being, then we will continue inshallah. Thank you very much.
10:26.